All right, so what we're going to look at here is how to graph surfaces in three-dimensional space. Now, we've already talked about how to graph a line in three-dimensional space. Now, that's not a surface. A line is a one-dimensional object, and it's determined by just that single parameter t, as we discussed in one of the previous videos. And because it's determined in terms of a single parameter, it makes it one-dimensional. Now, a plane is a two-dimensional surface that you can graph in 3 dimensions. If you can think, if you stood on the plane, there are 2 directions you can move, right? You can move north-south or east-west to walk around that plane, right? So it's a two-dimensional object. And there are other two-dimensional surfaces. Some of them are curvy, right? So let's look at a two-dimensional surface that we've discussed before. And we're going to look at the two-dimensional surface. Let me write this down and you can think about what this is going to be. Okay, x squared plus y squared plus z squared equals 4. What surface does that make? Well, if you recall, that is the equation of a sphere of radius 2. And so there it is. All right. And it is a three-dimensional surface. That describes not the interior of the sphere, just the very surface of the sphere. So in mathematics, if we were talking about the sphere together with its interior, what's inside of it, we would call it a ball, right? But if we say sphere, we're only talking about that very external shell that surrounds the ball, that is the surface of the sphere, the surface of the ball, that is the sphere. All right? So what I want to do, though, is I was wondering, what if we took off the z here? What if we looked at the surface described by x squared plus y squared equals 4? What would that surface look like? Well, I know that in the xy plane, I know what this describes. This describes a circle of radius 2. So if I look down into the xy plane, I should see a circle. But we're not specifying the z coordinate here. So while x and y have to live on that circle in the xy plane, the z could be anywhere. It could be any value. So what surface would that make? Think about it. Pause the video. Think about it. And I'm going to go enter that in here. Okay, did you figure it out? Well, this is what it becomes. It becomes this shape. And if you look down into the xy plane, I think if I push this button here and turn off perspective, you can see that it is a circle of radius 2. This is looking directly down the z-axis into the xy plane. As I tilt away from the z-axis, you can see that in fact it is a cylinder, right? And what's going on here is you can see that x and y have to live on that circle. But because z can be anything, it extends that circle vertically anywhere, to any distance, right? And so we end up with this shape. Now what if I change things a little bit more? What if I made it x squared plus z squared equals 4? What am I going to get then? Let's go in and think about that. Maybe pause the video, make a guess. Okay, well, here's what I'm thinking. If I'm saying x squared plus z squared equals 4, that should be a circle again in the xz plane. But y is not specified. So it should be the same thing but extended in the y direction. And that's exactly what we're seeing here. Notice it is again a cylinder. And if I look down let me spin it around a little bit so we can see it better. If I look directly down the y-axis, turn off perspective, that's what I see. It is the circle that we thought it would be, right? But because the y isn't specified in this equation, it extends infinitely in the y direction, right? And if I'll leave it to you to imagine what y squared plus z squared would look like equals 4 would look like. All right. Now let's look at some other surfaces. What if I did something like this? What if I did y equals z squared? So what kind of shape is this? Of course, that's a parabola. Now I'd like to graph this, but it does a pretty steep parabola, so let me put a 1/4 out front. All right, so 1/4 z squared, and that's still going to be a parabola. In the yz plane, that's going to look like a parabola. But x is not specified, right? So it'll extend infinitely in the x direction. So let's go ahead and take a look at this one. Here we have it. Right? It is there. You can see the parabolic shape here, extending infinitely in the x direction, right? But adhering to the shape of a parabola in the yz plane. And if I look directly down the x-axis, there we have it. That's the parabola, right, in the yz plane. And let's look at one more. What if I looked at x equals sine of z? What would this look like? Well, I know if I had an equation like y equals sine x, we know what that curve looks like, right? So this should be similar, but this is going to live in the xz plane. And because y is not specified, it should extend infinitely in the y direction. So let's go ahead and take a look at that one. There it is. Yep, it is reminiscent of a sine curve, as we can see by looking, if we look directly down the y-axis, you can see it looks like a sine curve in the xz plane, right? But if I tilt the view away from that, we can see it's that curve, but extended infinitely in the y direction. So these surfaces that we're looking at, these are all called cylindrical surfaces. And that means that it's one curve extended along a line. So in all these examples, the line was always one of the coordinate axes. Now you can go along diagonal lines, but that's a little bit more complicated. So I wanted to keep it simple and just look at these particular cylindrical surfaces. All right, the next kind of surfaces we want to look at are called quadric surfaces. Quadric surfaces are defined in terms of the variables x, y, and z and their squares. Right? So let's look at this example. All right, let's look at x squared over 4 plus y squared over 9 plus z squared over 25 equals 1. All right, what surface does this describe? Well, one way I would get at this is to look at what is called a trace. Traces are what you get when you set one of the variables equal to a constant. And a useful trace to look at is when you set a variable equal to 0. So let's do this. Let's set z equal to 0 here. Now what happens? Well, that makes all this disappear, right? So that means we just have this equation, x squared over 4 plus y squared over 9 equals 1. Now you should recognize this equation as being the equation of an ellipse. What ellipse is it? Well, let me go ahead and let's reorient this so that we're looking directly down the z-axis, right? So we're looking at the xy plane here. And I'm going to go ahead and plot this ellipse here. Right, you should be able to plot it like this. Now, how can I tell that that would be the way it would plot? Well, if I do this trace again and set y equal to 0, you see I have just this equation. And I see there's only two solutions, x equals plus or minus 2. Well, those are the 2 points here. So what am I doing? When I'm setting y equal to 0, I'm restricting myself to just the x-axis. So I'm finding the 2 points on the x-axis that intersect the ellipse, plus or minus 2. And if I set x equal to 0 instead, I can solve this. I have two solutions, y equals plus or minus 3. If I set x equal to 0, I'm restricting myself to the y-axis, so I'm finding just those 2 points, plus or minus 3, where the ellipse intersects the y-axis. So that is kind of an idea to get the dimensions of the ellipse. You just set one of the variables equal to 0 and find the solutions for the other one. And then you can fill in the curve in between. Now, you'd want to know that it's an ellipse before you fill in that curve, otherwise you don't know if it's doing something else. But at least you'll know what points it passes through on the axes. Now, what did we do here? We set z equal to 0. So what we're doing is we're finding the intersection of whatever surface this is in the plane defined by z equals 0. Well, that is the xy plane, right? So if I tilt, oops, I didn't mean to tilt like the, okay, I'm disoriented here. Oh, I see. Okay, there we are. Easy to get disoriented, and you know, I live in 3 dimensions. You'd think I'd be used to it by now. Okay, so that's what we looked at, right? So that's the ellipse. We're only looking at this in the xy plane because we're setting z equal to 0. So this is where the surface, whatever the surface is, it's going to intersect the xy plane along this curve. Now let's do another trace. Let's set y equal to 0. If I set y equal to 0, I get this equation. What is that? That is, again, the equation of an ellipse. So let's put ourselves into the xz plane. Okay, so I'm going to look down the y-axis here. And let's plot this guy. That'll be this one. Okay. All right. That's this ellipse. Let's see, if I set z equal to 0, I see the two solutions are x equals plus or minus 2. Those are those 2 points. And if I set x equal to 0, I see the two solutions are z equals plus or minus 5. Those are those 2 points. That's how I can quickly get the dimensions of that ellipse. But recognizing that this is an ellipse, I can then fill in the rest, right? So that is what the surface, that is how the surface intersects the, okay, I'm disoriented again. Let's put it like that. Okay, now I'm upside down. Okay, I got it. Okay, here we are. Okay, so that's how the surface intersects the xz plane. It intersects it along this curve. So whatever the surface is, it intersects the xy plane along that curve, and intersects the xz plane along the green curve. Now let's do one more trace. Let's set x equal to 0. Right? Set x equal to 0, we get the equation as follows. And again, that's the equation of, yeah, an ellipse. So if I look down the x-axis here, let's orient ourselves there, and I graph that ellipse, it would look like this. Okay, let's tilt out of this view. See if I can do this without getting disoriented. There we go, that was not too bad. So I can see how whatever surface it is, I can see how it intersects the xy plane, the xz plane, and the yz planes along these curves. And I think you can kind of tell what the surface is now, right? Yeah, it looks like an ellipsoid. All right, so let's go ahead and graph that full complete surface. If I can do that right there we are. That is what the surface looks like. So by looking at the traces where the surface intersects the coordinate planes, I can get an idea of what the entire surface looks like. And that's the idea of traces. Okay, now I want to change things around just slightly, all right? So I'm going to look at this equation. All right. All I've done is taken the same equation we looked at before, but changed that second plus sign to a minus. What happens here? Well, let's look at the traces. Okay, if I take the z equals 0 trace, what happens? Well, I get the same equation that we had before. So that's going to be exactly the same. So if I look into the plane z equals 0, that's the xy plane, I'm just getting that ellipse. All right, so just like we had before. Okay, well, that's what we get. Now let's look at the y equals 0 trace. So set y equal to 0, I get this equation. Okay, well, now this is not an ellipse, right? That's not a plus sign. You should recognize this as a hyperbola. And you can find the places the hyperbola intersects the axes in the exact same way that we did before. Let's go ahead and orient ourselves so we're looking right down the y-axis, right? So we're looking in the xz plane. And let's see, if I set z equal to 0, I see x is plus or minus 2, right? So it's going to intersect the x-axis here and here. If I set x equal to 0, what are the solutions now? Well, you might first be tempted to say plus or minus 5, but actually if you plug those in, it doesn't make this equation true, right? You get negative 1 equals 1. This has no solutions because the left-hand side is a negative number and the right-hand side is a positive number. So actually, you see that it doesn't intersect the z-axis at all. So when you graph this out, once you know it's a hyperbola, and you may need to, oops, that's not the right one. We're doing xz, right? So it's this one. You actually see that it looks like this. Okay, so now let's look at the, let's spin away from this perspective, this view. All right, so now we see that we got that, right? So that's what it's looking like. Now let's look at the x equals 0 trace. Okay, so now I got the equation. Okay, pretty much the same thing, except in the yz plane. So let's look down the x-axis. I get another hyperbola. So let's plot that out. There we go. You may need to review your hyperbola plotting ability, skills here. But there you go. So it's pretty much the same as we just saw. Let's rotate out of this view. And there it is. So that's what we're seeing here. Now, okay, I think I might see what's going on here. What I might want to know, though, is what's going on a little bit higher on the z-axis. So what you could do is look at something like z equals, let's do 5. All right, so let's see what happens when z equals 5. What would happen here? We're going to look at the z equal 5 trace. So this whole thing just becomes 1. So what I get here, I get a minus 1 equals 1, so that's the same thing as just setting it equal to 2. Well, what happens here? Now I'm looking down the z-axis here. Come on, let's look down the z. Come on, let me do it. Okay, there we are. What am I going to get? Well, this is an ellipse with a slightly bigger ellipse. If you graph this out, you'll see it's slightly bigger. I don't have it set to graph this, but you'll see, actually, maybe I can. Hold on. Okay, so I've gone ahead and graphed that. So it's an ellipse that's it's a little bit bigger. Now, one thing to note, though, is that it's actually the trace at z equals 5. So we're actually looking at the z equal 5 plane, the plane that's parallel to the xy plane, but passing through the z-axis at 5. All right, so not z equals 0, not down here, but up here, right? So it's actually, we're looking up a little bit higher. And so by adjusting the value of our trace number here, we can look at the intersections of the surface on different planes, right? You don't have to use 0. And you could do it z equal negative 5 too, and you'll see you get exactly the same thing because z is squared here, right? So you could imagine this same purple ellipse here down a little bit lower. And so what we're seeing here is this surface, right? And this surface is called a hyperboloid, right? Because it's comprised of hyperbolas, right? And so that is the surface that we've just described here.